let us complete the discussion that we have been performing over the last 2 modules. We are discussing second order nonlinear phenomena, and we have said without deriving that intensity of the second harmonic light is proportional to square of second order nonlinear susceptibility, length of the crystal, and something like sin square theta by theta square, where theta involves delta k and I 0 square of omega. And hence, we have said that in order to get favorable conditions for getting second harmonic generation is you should use a high intensity of fundamental light, you should use as much length of the nonlinear material as you can without messing up things. You should have a high the medium should have a high second order nonlinear susceptibility, and finally, delta k has to be equal to 0. That is what is going to that is what we are going to continue upon. Delta k has to be equal to 0. What is k? Is a vector associated with the wave, right, k vector. What is the meaning of delta k equal to 0? Momentum is conserved in the process of second harmonic generation. Total momentum of the combining photons is equal to the momentum of the second harmonic photon. Okay. So, from here the discussion we are performing is we want to know how it is possible to generate a second harmonic, because one problem we had faced already is that the refractive index of 2 omega has to be equal to refractive index of omega, and we have said in the earlier module that it is impossible to do it unless you have a birefringent crystal. So, what we are going to learn in this module is how is it that birefringence helps, and we have already talked about birefringence, but let us recap very quickly. Birefringence means this: you have a crystal which has an optic axis. Once again, we will tell you, we will discuss what optic axis is. When light falls on it, it gets divided into 2 parts. One of the rays that passes through is ordinary ray and the other one is extraordinary ray. In the ordinary ray, polarization is the same as the polarization of incident light. In extraordinary ray, polarization is perpendicular to that of incident light. And then the most important thing is that for ordinary ray, the refractive index of the material, please understand, the refractive index of the material throughout is the same no matter what the angle of incidence is. However, for the extraordinary ray, refractive index depends on the angle of incidence. So, now what we will do is we will try to draw polar plots with only one circle or oval shape, we will not draw contours or anything. We will try to draw polar plots of this refractive index for O ray as well as E ray, and we will do that for 2 different kinds of crystals, as you will see. So, let us say this is the optic axis. What is optic axis? We will come to it, wait a little longer. And let us say this is the angle of incidence. Okay. If optic axis is Z and I call this angle between optic axis and the incident ray theta, does that remind you of something? Optic axis I am calling Z and I am calling the angle between the optic axis and this incident ray to be theta. Does that ring a bell? Does that remind you of something? Earth theta phi. So, well, I have already said it is theta, right? No, position vector is done. This is theta, azimuthal angle, okay, azimuthal angle. That can be different, right? There is no special significance of making this theta small and making this theta large. All we are trying to say is, in principle, theta can be anything from say 0 to 180 or even 0 to 360 in this case. Now, suppose for every value of theta of pence, this is Z this is the incident ray, this angle is theta. So, for every value of theta, I am going to plot the refractive index, once for the O ray, once for the E ray, once for the ordinary ray, once for the extraordinary ray. Can you tell me what shape I will get for the ordinary ray? For ordinary ray, if I plot, so for this angle theta 1, I plot NO, then for this angle I will plot NO. It will be the same, is not it? Because remember, for an ordinary ray, refractive index is not dependent on the incident ray, incident angle, right. So, I will get a circle, yeah, and it is a polar plot. So, do not. So, I will get a circle like this. This is a circle I get for NO, where O stands for O ray, ordinary ray. If I want to make a similar plot for the extraordinary ray, what will it look like? For an extraordinary ray, remember, n depends on the angle of incidence. So, NE, if I call the refractive index of the extraordinary ray, if I denote it as NE, then it is going to have theta dependence. It is not going to be a circle. What will it be? Will it be a square? Will it be a triangle? Yeah, what should it be? Huh? It will be a distorted circle. So, it will be an ellipse, right? Because the point is this, let us say this is the this is theta, and let us say this is also theta, this angle and this angle are same. There is no reason why n should be any different for this position and this position, right. They will be same, but the moment you change, it will change in a different way. So, I am going to have an ellipse, but there are two cases that can be there. And this is a good time to learn what an optic axis is. An optic axis is the direction in which, if the incident ray propagates in the direction of the optic axis, then refractive index of O ray and E ray are equal to each other. Okay. No separation between O ray and E ray if incidence is along the optic axis. That is what optic axis is. Are we clear? Yeah. Have you understood? See, NO remains the same, NE does not, it changes, but at some angle of incidence, NO and NE are equal. That is a property that is there. Okay. So, that the line that you can get in that direction, that defines the optic axis, right. So, that is your reference. So, what I am saying is, with respect to optic axis, we are defining theta. When theta equal to 0, then NO equal to NE. When theta equal to 180, then also NO equal to NE. Okay. Now, with that I can draw two different ellipses. See, what I am saying is, at this point and at this point, NE and NO have to be the same. But what happens in the middle? NE can always be smaller than NO, or NE can always be larger than NO. If NE is always smaller than NO, then I get an ellipse like this. Okay. NE is shown in dashed lines. And in the other case, if, and at this moment I realize that at this point my animation could have been better. The other case is, for theta equal to 0, NO and NO is equal to NE, but after that NE is always more than NO, then this will be the case. Agreed? In this one, the first one, NO is greater than equal to NE. The second one, NO is less than equal to Ne. When is NO equal to Ne in both the cases? When is NO equal to Ne? Yes. When the incidence is along optic axis, or in other words theta equal to 0 or 180 degrees. Have we understood this diagram? Yeah. Now, let us get done with the definitions. In the first case, where NO is greater than equal to Ne, for those crystals you call them negative crystals. And of course, if this is negative, then the other one, crystals in which NO is less than equal to Ne, those crystals are called positive crystals. All right. Now, here let us say I have drawn this NO and Ne for the fundamental omega 1. Now, I will want to draw NO and Ne for 2 omega. But before going further, are we all clear? Have you understood this part? Have you understood what is going on? Because the next, we have introduced one phenomenon already on this slide. Now, after this, we are going to introduce another phenomenon, and they will add up to provide the condition for angle tuning for phase matching. So, it is important that we are all on the same page at this point. Is there any question? Is there any doubt? Everybody has understood everything? Can I go ahead? Okay. Now, I want to draw the surfaces for NO and Ne for 2 omega. Okay, and let us say I will draw it for the negative crystal. You can draw it for the positive crystal yourself, and it is not very difficult also once we do it slowly. So, first of all, what will happen? Will a negative crystal become a positive crystal for the second harmonic, or will it remain a negative crystal? It will remain a negative crystal. So, you get similar kind of a diagram. Yes. Next question is, well, since NO is a circle, it is easier to talk about NO. Is NO going to be the same or different for 2 omega generally? It is going to be different, we have already said that, right. So, is the circle going to be smaller or larger? For 2 omega, is the refractive index larger or smaller than that for omega? It is smaller, always smaller. So, what I will do now is, I am going to draw that circle and ellipse for NO and Ne for 2 omega in the same picture. It's just that I will draw it in blue. Okay, understood? Let us go through this quickly once again. Have you understood this circle and ellipse business? For NO, the polar plot is a circle, because the refractive index does not depend on theta. Okay, the polar plot means for this theta, the tip of this pen will be at the value of n. So, if n is large, it will be longer, if n is small, it will be like this. Okay. So, since NO is the same for all values of theta, the tip of this pen is going to define a circle. However, for Ne, it is not going to define a circle. With increase in theta, it can either become smaller and smaller, but when it becomes 90 degrees, when it goes beyond 90 degrees, it will start becoming larger again until it gets the same value here. Okay. Or it becomes larger and larger until it reaches 90 degrees, and then it becomes smaller again until at 180 degrees it is equal. Okay. That is how we get these two pictures. The first one, where N0 is greater than equal to N1, why am I saying N1 and why am I saying N0, sorry, where NO, refractive index for the ordinary ray, is greater than equal to that for the extraordinary ray, those crystals are called negative crystals. And the second case, where the refractive index for the ordinary ray is less than or equal to that for the extraordinary ray, we call them positive crystals. So far so good, we have understood this diagram. Next we said, now for the negative crystal, I might as well have drawn it for the positive crystal, it does not matter. I am just showing you the example. For the negative crystal, now I want to draw the circle and ellipse for NO and NE, not for the fundamental omega, but for the second harmonic 2 omega. Okay? So, first thing we agreed upon is that this basic shape should not change. A negative crystal will remain a negative crystal, but then refractive index for 2 omega for the O ray, it is easier to understand the O ray. So, it will extend to E ray as well, will be smaller than that for omega. So, if I draw the surfaces for surface for NO for 2 omega, it is going to be a circle with a smaller radius. And what about the surface for NE for the second harmonic? It is going to be an ellipse, but a smaller ellipse. So, this is what I have drawn. If possible, try to not see the black picture, try to see the blue picture only. It is the same as the black picture, just smaller. Okay. Now comes the climax. Are you okay so far? Now see, look very carefully. There are 4 points at which NO for 2 omega and NE for omega have the same value. 4 points at which NO for 2 omega, the blue circle, has cut the surface for NE for omega, the black dashed ellipse. Is that right? I will show you one. Look at this point. Look at this point. And this is where it is important to understand polar plots, what it means. The distance from the center, that is the value, and angular displacement from z, that is theta. Okay. So, where the point where the blue circle and the black ellipse have overlapped is the point where their values are the same, or in other words, refractive index for the O ray of 2 omega is equal to refractive index of E ray of the fundamental. Okay? That is your phase matching condition. Remember, what was phase matching condition? That the fundamental and the second harmonic have to have the same refractive index. Here it is achieved. Okay. We set out with the problem that you take a regular crystal, the refractive index for 2 omega will always be less than refractive index for omega. But then that problem has been circumvented because of birefringence. Due to birefringence, you produce 2 rays, the ordinary ray and the extraordinary ray, right. While the refractive index of the ordinary ray does not change for change in theta, refractive index for extraordinary ray does. Otherwise, it would have been just 2 circles that would not overlap. So, because of this, because you have 2 shapes, you have an overlap, some points of overlap, 4 points of overlap to be more precise, 4 values of theta, at which the refractive index for the ordinary ray with frequency 2 omega has the same value as the extraordinary ray for light with frequency omega. So, phase matching condition is achieved. All right. Experimentally, how will I do it? What am I doing here? What I have discussed is, this is z optic axis and this is the angle of incidence. We are talking about increasing theta this way, no need. I can move the optic axis. How will I move the optic axis? I will rotate the crystal. For the same angle of incidence, let us say this is the optic, well, we are using this for the optic axis. This is the incident beam and this is the optic axis of the crystal, I rotate. I rotate until the appropriate theta value is achieved, where you have NO2 omega equal to NE omega, you are done. Okay. This is why we get second harmonic generation conveniently by simply rotating the crystal. What we are doing essentially is, we are changing the angle between the optic axis and the incident ray. Since Muhammad could not go to the mountain, mountain has come to Muhammad. Cannot change incident ray without messing up everything. So, we have just rotated the crystal. Now, remember, we had said something else. We had said that the polarization of the second harmonic light is perpendicular to that of the incident light. Do you see why? See, phase matching condition has been achieved between what and what? Omega 2 omega, I understand, but ordinary ray of omega and extraordinary ray of omega and ordinary ray of 2 omega. And as we have said already, O ray and E ray have perpendicular polarizations. This is why second harmonic light has perpendicular polarization with respect to the fundamental. Okay. Polarization of second harmonic light is perpendicular to that of the fundamental. Okay. So, so far so good, everything is looking nice. Concluding comment for today is this: nowadays, at least for commercial setups, you only have, everybody uses crystals with a single optic axis, uniaxial crystals. There are crystals which are multi-axial. Fortunately, people do not want to use them anymore. I have used, and believe me, it is a pain. Multi-axial means you have to turn not only along this, but also along this and along this sometimes. So, if that happens, you have more parameters, and the problem is you never know. You turn in one direction, you do not know whether you have reached the correct direction or not, because the other two directions or the other direction that is there may be way off. Okay. If you can get everything correct, then you will get very good second harmonic generation. But generally nowadays, in commercial systems, people do not like to use anything other than uniaxial crystals, for the simple reason that there is only one control. You turn in one direction, change this value of theta. So, you can imagine if there is another axis, what will happen? There will be theta 1 and there will be theta 2, and this theta is different from azimuthal angle, that in principle it can go from 0 to 360. Achha, I have shown 4 points, right, 4 angles at which you can get second harmonic generation. Do you observe that experimentally? Yeah, you do not, right? Usually you get only at 1, sometimes you get at 2. Why? Because what it means is, if you want to go to the other side, incident angle, instead of going this way, the light has to go this way. So, it is equivalent to turning the crystal completely. Who will do that? Nobody does it. So, generally there is one unique point where you can get second harmonic generation. So, that is the end of this 3 module discussion. What we hope to have achieved in this is that we have got ourselves introduced to this fascinating world of nonlinear optics a little bit without deriving anything. And secondly, we have at least understood one operation that we do regularly in lab, and that is happily turn the crystal and see that you get nice blue light coming out. Now, what we will do next is, second harmonic is done. In the next module, we will try to discuss a little bit about some frequency generation, and we will talk about 2 kinds of phase matching. And then we will go on to discuss the next step of second harmonic generation or some frequency generation, that is optical parametric amplification or optical parametric generation to start with. See, we are talking about generating some frequencies so far. It is also possible to generate different frequencies, difference frequencies. Okay. That is where we will get to, and then when we are done with that discussion, we will try to discuss what is there inside the optical parametric amplifier. And with that, I think our discussion of instruments will be more or less done. Then we start discussing actual experiments. We have already introduced pump probe, but then what we can do is we can start with the classic experiments of Ahmed Zuhail, then go on to other pump probe experiments. Then later on, we are going to talk about experiments that involve this nonlinear properties as well. We want to talk about Raman experiments and all. So, we will need this later on as well.